3D printing is in a bit of a graduation phase right now. When it was still very new, we were playing around with everything, not really knowing where the limits were yet. And once we had figured out those limits, well, we knew that PLA and PETG were the two materials that are somewhat easy to print, and anything that was more demanding usually wasn't worth the trade-offs. So for the longest time, we stuck to those materials. But now that we've got those really well figured out, we started to make use of that knowledge for the more demanding materials like extra wear-resistant filament, high-stiffness material like fiber-reinforced polymers, or the classic temperature-resistant materials like ABS, ASA, and polycarbonate. I've been sticking to PETG for probably more parts than I should have. It's mildly temperature-resistant, but very soft. So I'm wondering, are we at a point yet where we can confidently print those engineering type materials yet? These are the contestants that I'll be benchmarking against each other. In the orange corner, we've got the Core One and the Core One L. Both of these have the closable vent in the front and the exhaust fans in the back. And the L is obviously larger, but it also adds a high power heated bed that serves double duty as an active chamber heater with a pair of fans at the bottom. Also really strong magnets in the bed. In fact, that they're so strong that I can see some people struggling to lift the print sheets, but it does make sense. Even with PETG, the reason prints warp on my Excel is usually the print sheets coming up from the magnets. And in the green corner, we've got the P2S and the H2S. Similar relation here. Obviously, the H2S is larger and has active chamber heating, but using a dedicated heater fan. Both the H2S and the P2S can choose to draw in fresh air or to just circulate the chamber through their filters. On the Prusa machines, the filter unit is an optional add-on that sits on the back of the machine, but it is built in a way where any air sucked out of the printer needs to pass through the filter first. Filtration is one thing, and it's important for PC and ABS, as those have really nasty fumes, but air management is only one part of why a specific machine can or cannot print a part. The core aspect that we're fighting here is thermal expansion in one way or another. But because we're printing in layers, it adds up, and kids, that's where warping comes from. So really simplified, let's say that our polymer, our filament, has two really discrete states, solid and liquid. In reality, it's not as simple, but hear me out. In either state, the plastic will want to expand when it gets warm and contract when it cools down. So the printer lays down a bead of hot plastic onto either the print bed or some area of the printed part, and that fresh bead will immediately start cooling down and will want to start contracting. But because we just welded one side onto something that is already solid, ideally, and our bead itself is still liquid and therefore soft, it can't really do anything. It doesn't have the rigidity to exert force. So as it cools down, its volume will still shrink, but all of that shrinkage has to happen in the z-axis, where it's not really that critical. But things change once that bead gets to the point where it turns solid and hard and can finally produce some force externally. Again, this is simplified. Unlike metals, plastics don't have a single temperature where they go from solid to liquid. It's a continuous, gradual process. And even seemingly hard metrics, like for example the glass transition temperature, that only tells you when that process happens the quickest per degree of temperature change. But let's stick with the simple model because it does work really well here. When that bead becomes solid, it will of course want to continue shrinking as it cools. And now it is rigid enough to start tugging on things. Anything that happens above that temperature, we can sort of ignore. But with every degree that it cools off below that temperature, now adds up layer after layer after layer. And when you're printing onto a layer that has already shrunk a certain amount, and you're now adding a fresh layer that is going to shrink again, you get that characteristic banana-style warping. The biggest weakness of PLA is also its biggest strength, and that's that its transition from soft and liquid to hard and solid happens at a very low temperature. So most of the cooling, and therefore most of the shrinking it wants to do, happens while it is still soft. That makes it super easy to print without any chamber heating or temperature control. But it also means that printed parts are super easy to melt in the sun or in a hot car. On the other extreme, something like ABS or polycarbonate has that transition point quite high. So the final part stays usable in higher temperatures, but it also means that if you print it with the same sort of outside parameters as PLA, and let the layers cool down quite far during the print, much more of that cooling and shrinking is now happening in a temperature range where the plastic is already solid. So you get much higher forces adding up. The two common ways to deal with this shrinkage are either by using a filament that, for the same amount of temperature drop, just doesn't shrink as much. And this is the huge reason why shredded carbon fiber helps with this. The carbon fiber itself actually has a slightly negative coefficient of thermal expansion. So as the carbon fiber in here cools down, it actually wants to grow, it wants to expand. And because that fiber is also incredibly rigid, that means it can negate quite a bit of the expansion that the base polymer wants to do. The other option, of course, is heated chambers, which all these printers sort of have. So you keep the filament the same, but you change how far you allow it to cool down before the next layer is added. And then once the part is finished, you take it out of the printer, where the printer itself cools down, and all that shrinkage and cooling happens as a unit in the finished part, but it doesn't have those internal forces adding up that would cause the part to warp. The ideal scenario would be if we could instantly cool the fresh layer to exactly the temperature where it gets solid and then perfectly keep it there for the rest of the print. But in reality, because it's a gradual hardening process, even freshly printed filament still has some rigidity and can produce some force. And if you keep the already printed layers at too high of a temperature, that can be enough to cause what's known as curling, where, for example, overhangs are too soft and get pulled inwards by the fresh layer. On the other hand, if you cool the layers too much, now the next layer isn't going to bond to it that well anymore, and your part is going to start cracking and delaminating at the layer lines. That's something that is very common with ABS. Figuring out those universally usable printing profiles for high temp filaments, or even for tricky situations with your regular filaments, is a challenge that is as old as 3D printing itself. And more recently, we've seen some better software control in the slicers that help with some of those compromises you'd otherwise have to make. For example, Prusa Slicer now has much more fine-grained control specific for how it prints overhangs. So they can better optimize the profiles to work for everything else in the print. And then if those settings are causing issues for overhangs, they can tune in just that one aspect separately. This is the part that I printed, laying down like this. It's part of a filter holder box, goes in like so in the back here and props these up so I can fit in a massive filter without printing the entire thing on the Excel. Just like that, glue in some panels here, save some filament. And for this, I did 4 different test prints on each machine, using the same print settings and the closest filament preset that I could find for the filament type. For filaments, I used ColorFab XT, which is a hardcore PTG, then Azurefilm ABS, which is really just a standard ABS, Prusa PC Blend, which is a more easily printable version of polycarbonate, and finally Polymaker PC Plus, which is a lot closer to pure plain polycarbonate. And while these are printing, let's check out this video sponsor, PCBWay. One of the harder lessons that I had to learn, and that I'm still struggling with, is that as a maker, you don't have to do every part of the process yourself for it to still be your project or your thing that you built. I know how interesting it seems to have your own CNC router, pick and place, laser cutter, 3D printer obviously, but for getting stuff done, you're just gonna get a better final result and also save yourself a bunch of time if you outsource the really specialized parts. And PCBWay does just that. The biggest revelation for me has been ordering populated SMD boards. They're so much nicer than soldering your own through-hole parts, and trying to get good at placing and reflowing SMD is a whole hobby by itself. PCBWay also offers CNC routing, milling and turning, does 3D printing from standard and specialized materials, and even does sheet metal work, which is a pretty rare offer. If you value your time at all of these end up being cheaper than trying to figure it out yourself. So check out PCBWay as your project partner at the links below. And if you need some inspiration, check out the project sharing section at pcbway.com/project. So these are done, and you may have noticed the Core One L having some issues there in the end with the polycarbonate materials. We'll get to those in a second. These parts are all labeled on the bottom, and I want to try and rank them from best to worst, basically blind to which machine these were printed on. Let's start with the ColorFab XT, and this one unfortunately has some print issues, so I know which printer it is. These other 3 though look pretty much identical. I think there's some difference in, so there's a little bit of a ridge there. This one has nothing, and this one has some ridges visible. So I would say this one is like the best, and these two are pretty much equal. We should also look at how much these warped, and there it is pretty obvious this one warped more than that. So I think this is going to be my ranking for the ColorFab XT. The worst one here is the P2S. It looks like the hot end was struggling. The next one up is the Core One. Still warped a little bit, but overall pretty good. Then we've got the H2S and the Core One L at the top. These two pretty much identical, though the Core One L did warp a little less actually. Then moving up to ABS, and this one and this one. These two have some obvious overfilling at the top here where you can see that it was warping so much that now the nozzle was dragging through the filament. So these two are definitely, well, one of these is the P2S, the other one is the Core One, because those don't have an actively heated chamber. This one though looks a little worse. It has much more visible warping. We can see that on this side here as well. This one just, yeah, these two are sprung up quite far. These next two, so H2S and Core One L, which one is which, I don't know, but honestly, they look pretty much identical here. Maybe this one has a little more warp. Yeah, by the slightest amount. Let's check out the ranking. The worst one is the Core One. You can definitely see where the part was sticking to the bed and where it was lifting. There's even two lines on this other side here. And yeah, this has quite the amount of curl. The next one up is the P2S. More even warping, but still pretty crooked. Then we've got the Core One L, and it is beat by the H2S by the smallest margin. Then the Prusa PC blend, and again this one is very much overfilled at the top, so this was warping quite a bit. And this one as well, but not as extreme. This one still has visible overfilling, and this one is underfilled at spots. So yeah, none of these are great results. And in fact, these pretty much all warped except for this last one at the end here. This one is still a little warped, but mostly flat. So the worst one here is the Core One L. And yeah, you can see how much of a banana that actually ends up being. Then one up from that is the P2S. That is still a part that is not very usable. You can see how much it actually ended up warping up here. So that's a good 3 or 4 millimeters. One up from that is the Core One. Again, with the distinct separation lines where it stuck and where it lifted. And then at the top, the H2S. So this is the only one that is like reasonably flat, but still at the ends, you can see that it kind of is coming up here and still warping. And finally, the Polymaker PC Plus. This one though is the one from the Core One L that I manually adjusted the settings for, so that's not a fair comparison. The fair comparison would be these, that all of them failed. So these were 3 tries with the same settings. None of them stuck particularly well. They were pretty flat, but they came loose from the bed. For these other 3, well, these 2 are clearly warped. This one is flat, so well, I guess this one must be the H2S, and it is. These 2 though, I don't know, both of them are warped pretty heavily. This one has a little more warp than this guy, and that is the P2S. And the Core One actually held on just a little bit better, but again, not really what I would call a good usable print. So how did these printers do? Well, the H2S was really consistent here. It did have, I think it's this part, it did have a corner right here where you can tell it was going too fast around that corner, and it's sort of under extruding, but otherwise, yeah, good job, really consistent. At least for XT and ABS, the Core One L also did a pretty good job. I should mention that I used the satin PEI sheets on the Prusas for these materials. That's what they recommend. Bamboo was on the standard textured PEI, which they greenlight for pretty much all materials. Between the Core One and the P2S, pretty much all the parts had some very noticeable warping to them, which makes sense. These are not actively heated chambers, and the best you can hope for chamber temperature is 40-45 degrees. It's not nothing, but it's pretty far off from the 60-ish degrees that the 2 actively heated printers manage. The Core One did just a little better than the P2S, but neither one was great for these high-temp materials. They all had warping, and you're looking at printing with a brim or just sticking to much, much smaller parts if you want them to be usable with these high-temp materials. For some reason, the XT print on the P2S looked like it was printed way too cold. It had all these little, flaked off bits on it, even though this is the same profiles as on the H2S. Of course, the one that's sort of standing out, and not in a good way, is the Core One L. This was the only printer that, without manually tweaking things, just couldn't handle printing polycarbonate at all. And both the Prusa PC Blend and the Polymaker PC Plus. And this should not be the printer that's having issues here. Of course, the Core One L has a much more powerful heated bed now, the first Prusa machine to use a 230 volt heater, and it uses that heater to actively transfer heat from the underside of the bed into the chamber air with 2 fans underneath the bed. But it doesn't look like that was actually helping much. There were 2 issues that I think were compounding to cause its poor performance here. The first one were these dots on the print bed. From what I can tell, these are grease drops from the lubrication that the factory applied on the linear rail of the toolhead. As the chamber gets hot, and that rail gets hot as well, grease tends to get soft and liquid, and it just ends up dropping onto the bed, which obviously is not a thing that ends up improving bed adhesion. It also seems to be going pretty much everywhere, and in fact, even touching these prints, they feel greasy. After a couple of these failed polycarbonate prints, I was noticing that the front door was super smeary and basically coated in a grease film. I tried cleaning the bed, wiping it down with ethanol again, but it did not improve things. The other thing I was suspecting was that the new heated bed construction may not be optimal for actually keeping the bed surface at temperature. To get some comparative and objective numbers, I applied some of my super matte gaffer's tape to the print beds of all these machines. In the past I had spray painted some of these beds black, but that kind of ruins them and I still want to use these. The reason for that is that thermal cameras need a consistent surface to measure against, and to get the temperature, I started the print cycle and let the machines heat up to the set bed and chamber temperatures. The 2 bamboo machines were actually pretty hot, with the H2S landing at the exact 110 degrees set bed temperature, while the P2S was displaying 100 degrees, but the surface was actually already at 105 degrees. The Core One was displaying 100, but actually was sitting around 105, and the Core One L was displaying 110, but the area we were printing to was actually around 96 to 98 degrees. Notably though, the Core One L had visible cold spots, exactly at those spots where the fans were blowing against the underside of the bed, and the sides of the bed were 5 to 10 degrees hotter. I don't know if the poor bed adhesion was just a combination of the grease fouling and the over-reported bed temperature, or whether the actual airflow from the bed fans also caused some sort of unfortunate draft that was cooling down, the part at the front of the bed as it was printing, so, it was warping more than it should. The unfortunate correlation here is that the more the chamber heating bed fans need to work, either because you want to have a higher chamber temperature for a higher temp material, or because a colder ambient temperature means the printer is losing more heat through its shell, the more energy those fans will need to extract from the heated bed. So with that hybrid bed heater, you always trade chamber temperature against a consistent bed temperature. And of course, the Core One L side panels are now made of aluminum instead of steel, as on the original Core One. So the Core One L ends up losing quite a bit more heat through that more thermally conductive shell. Knowing that those cold spots exist, I retried the print in the center of the bed with the ends oriented towards the hottest part of the bed, which are in the center to the left and right. I also manually adjusted the bed and chamber temperature to their maximum, which is 120 degrees and 60 degrees respectively. The bed had no problem at all getting temperature, but the chamber really slowed down in heating past 56, 57 degrees. The basement studio was, set to 18 degrees room temperature for all these tests, but if you had your room closer to 22 degrees or more, which is quite cozy warm, it should be able to make it to 60. But when the bed is set to anything lower than its maximum 120 degrees, the temperature that the chamber can reach and maintain also drops proportionally. Maybe wrap the Core One L up in the blanket, but do keep the electronics vents open. Either way, this print worked with the manually adjusted settings, and it compares pretty well. Of course, that does bring us to the age-old question of whether print profiles that give you predictable results should be considered as part of the product and the thing that you buy and pay for. And my stance for the longest time now has been that yes, they definitely are part of what you are expecting from a printer. Cranking up the temperatures like I did on the Core One L is a rather small correction. It's certainly one that is very dependent on the exact filament you choose, but considering that all the other printers did a much better job printing the same polycarbonate with their generic stock settings and even using technically inferior setups, I just have to wonder why the Core One L didn't just add a dedicated chamber heater. These are not that expensive. I mean, for reference, you can get full little plug-in PTC heaters with a fan and temperature regulation for less than $10. And I don't see how these would be difficult to integrate into the printer. Everyone else is doing it, and the Core One L already has that extra layer of AC safety cutoffs that that extra heater could just tie into and share with the bed. The whole situation just reminds me of the little mini heater beds that the Prusa XL uses, where I was already questioning how it was at all viable to use 16 individually controlled heated beds. And Prusa was like, no, this doesn't make the printer any more expensive. But then the Core One L, in fact, did not use the same heater tiles in, for example, a smaller 3x3 grid, but they went with a standard silicone heater mat. And the Prusa XL ended up being the only printer where they ever made use of those heater tiles. Now, the Core One L is the first printer from Prusa where I think you notice that they were definitely optimizing things for cost, which absolutely is a good thing. But still, these fans feel more like an afterthought than anything. To get back on topic of which of these printers can actually handle high temperature materials, honestly, they all did a pretty surprisingly good job, better than I was expecting from them. Compared to the benchmark of having open frame machines that are all just running in ambient air, these all did a fantastic job printing materials like ABS and polycarbonate. I did not print the same test on something like a Mark IV's, but speaking from experience, I don't think any of the open frame machines would handle printing these parts in any of these materials. Layer adhesion on ABS is and always has been a problem, and it is on these prints too. Pretty much you can print these with a slightly higher nozzle temperature, raise the ambient temperature a bit. I didn't see any artifacts that would hint that these are already running at their limits. But yeah, this is just an issue with ABS. The other materials are a lot better here. Polycarbonate, much better layer adhesion. I think both the jump from the P2S to the H2S and the Core One to the Core One L, where the larger machines add some measure of active chamber heating, just makes sense, because the small machines printing small parts do an okay job here, again for smaller parts, but larger parts also will warp more, so you need to pay even more attention to parameters like controlling the chamber temperature. And I really do like seeing that even pure-ish polycarbonate is now totally printable on the heated chamber models. This stuff is pretty cool, of course. I mean, it's a high-temp material, but it's also super stiff. Compare that to the Colorfab XT. This sounds like wet paper. So mechanical stuff, robot arm joints with a built-in motor mount, this might be a really good option. As always, all the links to the machines and the materials are below. Thank you all for watching. Massive thanks to everyone who's already subscribed. Get subscribed if you aren't yet, or is even supporting the channel on YouTube memberships or Patreon. And for all of you, keep on making, take care of yourselves, and I'll see you in the next one.